Imagine you're watching a single marble roll toward a wall with two holes in it. You'd expect it to go through one hole, right? That's what physicists in the 1920s expected too. Because back then, they pictured electrons as discrete, hard little particles, basically tiny billiard balls, and figured they'd pile up behind each hole just like marbles would. So when they fired single electrons at that same setup, one at a time, they waited for exactly that. Two neat piles of marks, one behind each hole, nothing else. What built up on the screen instead made no sense at all. A pattern that could only happen if each electron had somehow passed through both holes at once, like a wave rather than a marble. That wave-like behavior wasn't just a quirk of one strange experiment. Physicists in the 1920s were already seeing hints of it elsewhere. And in 1927, a pair of researchers accidentally confirmed it by bouncing electrons off a nickel crystal and watching them diffract, spreading out in a pattern identical to how light bends around obstacles. Electrons weren't just acting a little bit wave-like. They were doing exactly what waves do. So when they set up the double-slit experiment, the prediction felt obvious. You've got a barrier with two narrow slits cut into it, and a screen behind it to catch whatever comes through. If you fire a marble at that barrier, it goes through one slit or the other, lands on the screen, and over time, you build up two piles of marks, one behind each slit, nothing else. That's all a solid object can do. They ran the same setup with electrons, firing them one at a time, so there was no chance of electrons bumping into each other and doing something weird as a group. They expected two piles of marks to slowly build up, one behind each slit, just like the marbles. Instead, what appeared on the screen was a series of alternating bright and dark stripes spread across the whole surface, and that pattern had no business being there. If electrons were solid objects, because a solid object going through one slit can't possibly know the other slit exists. To understand what that stripe pattern means, think about dropping two pebbles into a pond at the same time, close together. Each one sends out ripples in all directions, and those ripples spread out and run into each other. Where two peaks meet, their amplitudes add up into a bigger peak, and where a peak meets a trough, the amplitudes subtract and cancel out, leaving the water flat. The result is a pattern of churned up water and calm water in alternating strips. That's an interference pattern, and it can only happen with waves. The striped pattern on the electron screen is built by the exact same math, so the electron wasn't arriving as a point moving through one slit. It spread out like a wave, passed through both slits at once, and interfered with itself on the way to the screen. Physicists thought maybe it was a group effect, so they slowed the experiment way down, sending electrons through one at a time with long gaps between them, and watched the screen dot by dot. Each individual dot landed in what looked like a random spot, but after hundreds of dots accumulated, the same striped interference pattern appeared again. And it doesn't stop at electrons. Researchers have since run the same experiment with atoms, and even with buckyballs, molecules made of 60 carbon atoms with a mass of around 2,000 atomic units. Can you imagine something that large? A molecule you could almost draw on paper, rippling through both slits at once. The interference pattern showed up there too, which means this isn't a quirk of tiny specks. It's a property of matter itself. So the obvious question at that point is, if the electron really is going through both slits at once, why not just watch it? Scientists did exactly that. They set up detectors at the slits, turned them on, and waited to see the interference pattern still show up. Instead, the stripes vanished. Not faded a little, not got blurry around the edges. Gone. What appeared on the screen were two clean piles of marks, one behind each slit, exactly what you'd expect from a solid marble going through one hole or the other. Turn the detector off and the stripes come back. Turn it on and they disappear. And labs around the world have repeated this result for decades and always gotten the same total collapse of the interference pattern. The tempting explanation is that the detector must be bumping the electron somehow, nudging it off course, disturbing it just enough to wreck the interference. But that's not what's happening. This was actually the center of a famous argument back in the 1920s, when Einstein proposed that you could detect which slit a particle used by measuring the tiny recoil force on the slit itself, like a spring shaking when something passes through it, and still preserve the wave pattern. Bohr's counter was that any interaction capable of recording that recoil, any physical process that leaves a trace, must wash out the stripes. And Bohr was right. Even when researchers use detection methods that cause the smallest possible physical disturbance, ones that barely interact with the electron at all, the interference pattern still disappears the moment any path information gets recorded. What matters isn't the mechanical nudge. It's the fact that measurement is an active process, an irreversible magnification that creates a physical record in the world. And the degree of that record matters. If a sensor is only 50% effective, catching which slit the electron used only half the time, you don't get full stripes or no stripes. You get something in between, a partial pattern, faded and washed out in proportion to how much path information was captured. The more the detector knows, the less interference survives. When the detector registers which slit the electron used, that fact becomes encoded in the physical state of the detector itself. The electron and the detector are now linked, what physicists call entangled, and that link is what kills the interference. For the two paths to produce interference stripes, they have to be truly indistinguishable in the system's wave function, because the wave traveling through slit 1 and the wave traveling through slit 2 need to overlap and mix without any way to tell them apart. The moment the detector tags one path, the paths become distinguishable, and the mixing stops. Think about two identical musical notes played at the same time, blending into a single sound. The moment you can tell the notes apart, the blend breaks, because interference depends on the two waves being indistinguishable in the wave function. And exactly the same rule applies to electrons. So observation in quantum mechanics isn't passive. Gaining information about a system changes what that system physically does, and that raises a question that follows naturally from it. If electrons behave like waves, do those waves have a measurable size? Louis de Broglie had an answer to that in 1923, though most of his peers thought the idea was speculative at best. He proposed that if light could behave like a particle, then maybe every particle could behave like a wave. Not just electrons, but everything, and that each one had a wavelength you could actually calculate. The equation he wrote down fits on a sticky note. Take the momentum of an object, which is its mass multiplied by its speed, and divide Planck's constant by that number. The result is a wavelength. Written out, it's lambda equals h over p, and it doesn't have an asterisk saying it only applies to tiny things. It applies to everything. That's where it gets strange. You can plug your own mass and walking speed into that equation and get a wavelength back. It won't be zero. It'll just be so unimaginably small that no detector ever built could come close to measuring it. For an electron moving at a typical speed inside an atom, the wavelength you calculate comes out roughly the same size as the gaps between atoms in a crystal lattice, and that match isn't a coincidence. It's exactly why electrons fired at a crystal produce interference patterns. Neutrons do the same thing, and neutrons carry no electric charge at all, so it can't be an electrical effect. What matters is momentum, and neutrons moving at the right speed carry a de Broglie wavelength that lines up with those same crystal gaps perfectly. Now try the same calculation for a 10-gram bullet or baseball moving at normal speed. The wavelength comes out around 10 to the power of negative 34 or 35 meters. An atom is roughly 10 to the power of negative 10 meters across. That gap is so enormous, the wave behavior becomes purely academic, not just undetectable, but irrelevant in any practical sense. So you don't diffract around door frames or tunnel through walls because your wavelength is so tiny compared to any gap or surface you'd ever encounter that the wave behavior never gets a chance to show up. The math still applies to you. It just produces a number that means nothing at human scales. What de Broglie's equation actually did was draw a line between the quantum world and the everyday world, not by saying the rules change, but by showing why the same rules produce completely different results at different scales. When physicists applied this to atoms directly, something clicked. Treat an electron orbiting a nucleus as a wave wrapping around a closed loop, like a circular guitar string, and only certain wavelengths fit neatly without the wave running into itself and canceling out. Those stable fits, where a whole number of wavelengths completes the loop, correspond to specific energies, and that's exactly why electrons in atoms only occupy certain energy levels. Bohr had the right numbers for those levels years earlier, but no physical reason for why only certain orbits were allowed, and this was it. What that tells you is that the wave behavior isn't a quirk of the double-slit setup. It's baked into what matter actually is, at every scale, including yours. So an electron isn't a wave pretending to be a particle, or a particle pretending to be a wave. It's one thing that behaves differently depending on how you interact with it. And that's not a dodge, that's just what the experiment shows. Every object you've touched today has a de Broglie wavelength, and yours does too. But your mass is so large that your wavelength shrinks to a size no instrument could ever detect. So you'll never see yourself ripple. You're physically a collection of waves that can't produce wave behavior at your own scale. That idea of being one thing with two faces leads straight into the next question, which is what the wave actually is, and what it means for something to exist in two states at once before you measure it.